Okay, so before I move to the slides, let me share a screen about the book. Where's the book? Give me 1 second. Where is the book? Okay, yeah. Okay, so this is so today and also tomorrow we'll continue to learn about the dislocation. Okay, can you hear my screen? Okay, dislocation as well as a strengthening mechanism, and after that we'll move to the next chapter about failure. Okay,
Orang
so
ngirim pakai emoji dia ini. Justice.
okay,
Ini
siapa nih?
udah. Kenapa bisa gini?
Right. Okay, so this photograph. Let me make it bigger. Okay. Okay, so this photograph tells you about a microstructure. Okay, so if you look at the B over here, the picture B, it is a slice of a very thin can, and then they mold it into a storage like this. Okay, so so figure B is a partially formed aluminum beverage can. Okay, and then wait. Okay, and after that, so if we look at the microstructure, so you cut some of this a slice, yeah, and then you put it under microscope, under electron microscope. In microns, you will see this a picture, and this picture will tell you about the grains. Okay, so a very tiny this is actually 1 grain, 2 grain, and so on. So this is the grains. Okay, so the figure A represents the presence of aluminum grain structure. That is, grain is equi-X, having approximately the same dimension in all directions. Yeah, it's not round, but I think the diameter is quite average. Okay, and after that, what they do in the aluminum can processing, what they do is they pull it. Okay, so in figure C, it shows a completely formed beverage can. So from this one here, it is pulled up into a plastic deformation, and then what happened is, with the plastic deformation, all of the grains here is, and if we check it with the electron microscope, it will also pulled here, is also stretched, okay, and then they're also elongated. Okay, so if you look at the picture D over here, the grain of aluminum structure in this wall will change shape, and also they elongate in the direction of stretching, in the direction of those pulling. Okay, and the resulting grain structure will be similar, shown in this figure D, and then and in the properties, the resulted properties, the area of the grain boundary is also become stretched and also become elongated. That means the area between two boundaries will also increase. Okay, and a good thing about grain structure is actually, if you have grain boundaries, the bigger you have, the increasing you have of the grain boundary, it will it will actually uh, avoid the yielding. Okay, or and in other words, it will make it stronger. Okay, so that means this is one of the how to strengthen the metal, how to strengthen the mechanism of the metal is by pulling or by stretching. So you have a formed or a stretch metal, and then so one thing, you just need to have a small mass of that, yeah, a small piece of metal. That means also small piece of cost as well. And the second one, you will have a stronger material because of those strengthening mechanism, right? Okay, so that is the in this book, in every chapter you will have some description in the beginning. I'd like to explain to you about that one, so at least you know the bigger picture, that big elephants, that what's we're gonna learn in this chapter. Right, okay, so and then I'm gonna move into the next the one drive or the slides. Okay. Okay, still waiting quite a while. Or, okay, wait, still downloading. Or I think I'll just use uh, my laptop then. Okay. Yeah. Okay. So in this picture, so one of the application of plastic deformation is also the, maybe I can use also pointer. So this is also an example of plastic deformation. So we actually make it a plastic deformation to make pipe. So the pipe is actually based on a flat piece of metal, and then they pull it like this, so it become the the pipe like that. Okay, so we know that a plastic deformation is permanent, and strength and hardness also measure of material resistant to this deformation. Okay, so and then in microscopic scale, plastic deformation corresponds to the net movement of large numbers in response to applied stress. Okay, and then the difference between plastic deformation and elastic deformation, the interatomic bonds must be ruptured and then reformed. Okay, and then we also have learned about plastic deformation before in the defect, yeah, in the imperfection chapter before. Okay, we know about the dislocation, so I think I'm gonna skip this one, the Carter dislocation as well. Now I would like to uh, introduce you about the slip system. Okay, so what is a slip system? So the dislocation will move if there is a slip plane. Okay, so the dislocation doesn't move anywhere they like, but there is a preferred plane. Okay, and the preferred plane is actually there a specific direction along dislocation motion occur. Okay, so the dislocation actually will occur on a preferred plane. okay, and the plane that is preferred for the dislocation for the moving that one is called slip plane, okay, and then it will follow a direction which is called a slip direction, okay, and the combination of the slip plane and also the slip direction is termed a slip system, okay. And then the slip system, it depends on the crystal structure of the metals, and also it is atomic distortion that accompanies the motion of dislocation is a minimum. So usually for a particular crystal structure, the slip plane must be the plane that has the densest atomic packing. Okay, so it should have the highest planar density. So you have to think that, okay, so for example, I have BCC over here, so you have to think what type of which plane that it has the most dense of atomic packing, okay, is it in 100, okay, or is it in 110, or is it in 111, or in any other crystal structure, okay. Remember, we have learned how to read the plane, the the plane, yeah, the how to read the plane, okay, and also the crystal direction, crystal plane. So that is one of the purpose for learning that one, okay. So the slip plane is the plane, so I think I can make a highlighter here. So the slip plane, okay, so is that the plane that has the densest atomic packing, okay. And the second one, the slip direction, is also the direction that in that plane that has the most closely packed with atom, or with has linear density. Okay, so for example, this one, you can see FCC structure, this one here. So this is a FCC, a face center cubic, okay, face center cubic, 1 2 3 4 5 here, okay. And if you look at closely, or if you have the 3D models, in this one I have the 3D model for BCC, not FCC. I think I should find the FCC one. We see that this one, the set of plane of 111, okay, or is actually this is our close pack, okay. This all the close packing. So this is the plane for 111. So remember how to find the plane, the crystal plane, okay, 111. So this is the that is sliced through this point A, D, and F, okay. And if we slice them and then put it like this, it's gonna be looks like this, okay. So this is actually the most dense plane in FCC, okay. So a 111 type plane is indicating in the unit cell, for example in this figure, and the plane is positioned on the plane on the page, with the atoms now representing touching the nearest neighbor, because now all of the atom touching the nearest neighbor, so it's gonna be easy for them to do the dislocation, to do the plastic deformation, okay. It's easy to have cut with all of the neighboring atoms, and then break the bond, and then form a new bond again, and then makes like the dislocation like that, okay. So and then, so this is the slip plane. So the slip plane is called the 111 family. Okay, how about the direction? The direction is actually also the direction, which means that when all the linear density or the atom is at the densest. Okay, for example, we can't do for example 11 or 100. Okay, like this, for example. This one is quite it's not that packing as this one. So if you look at here, the most dense of the direction is in this direction, okay. This is also the most direction, or in this direction, or in this direction, because it is full of those atoms, okay. And if you try to calculate what is this direction or what is this direction, it actually will occur at 110, Okay, because it's basically this direction equal to direction and this direction as well. So it is slip will occur around 110 type direction and then within 111 planes. Okay, so then the 111 direction and the 111 plane and 110 will represent the slip plane and direction combination. Okay, or the slip system or FCC. Okay, if you look at here, it's only have one, but actually we can make let's say it can be like this one as well, right? Okay, so we have two. We will have two plane, or for example, how about if I started from here? For example, started from here and then up to, or maybe just with different color. How about from here and then to there and to there? It can be also possible. Okay, what happens if I start, for example, from with different color again, from start from here and then to here and then to there. I think this one should be that one, yeah. Okay, okay, so that's also quite similar. Okay, so for example, if you try to combine all of them, that would be 12 slip system, which is actually a multiplication of 4 unique 111 planes, and then there are 3 independent 110 direction. Okay, so all of the dislocation will just occur on those slip planes. Okay, so that means the more slip system metal have based on the crystal structure, then it will most likely to do some more dislocation. If it is more dislocation, that means the metal is easier to do the plastic deformation, and if the metal is easier to do plastic deformation, so then the metal is gonna be more ductile. Okay, it's less stronger. Okay, so for example, an example of FCC is aluminum. Aluminum has FCC crystal structure, and then if you look at the problem, if you look at this one there, it looks quite ductile because it has so many slip systems, so it's easy to do the plastic deformation. Okay, so you can see here in the slip system, in the face-centered cubic, we have a copper, aluminum, nickel, argentum, and aurum, the silver and gold. It has a slip plane. Okay, so face-centered cubic, so it has a number of system 12. And then here we have body-centered cubic for this one. Yes, so we have typed that one quite big. And then for hexagonal closed pack, it has less slip number of system, and for example titanium and magnesium. So we know that titanium is a very hard and strong metal. Okay, so the metals with the BCC and FCC structure, it will have a relatively large number of slip system, at least 12, and then these metals are quite ductile because extensive plastic deformation normally possible along the various system. Okay, conversely, ACP metals having active slip system are normally quite brittle. Okay, so here is the again go back to the previous one, the plastic deformation of polycrystalline material. So during the deformation, the integrity and the coherency are maintained along the grain boundaries, and then the deformation of individual grain is constrained by neighboring grain. Okay, and if you stretch them out, this grain, and you stretch them up to like this, the polycrystalline metals are stronger than single crystalline crystal equivalent, which means that the greater stress are required to initiate slip and attended yielding. Okay, this is due to geometric constraint imposed on the grain during deformation. Okay, so while we know that it is ductile material, sometimes we want the ductile material, but sometimes we want a stronger material. So if we have those ductile material, for example this aluminum can, what we can do if we stretch them, or if we call it foam, so it can stretch, and then all these lines or all these surface gonna be elongated, and once it's elongated, then it's gonna be stronger. Then it's gonna be stronger because we have a longer grain boundaries. Okay, so we will have, and then if we have, so we have learned about the mechanical properties of metal. We learn about the strength, the hardness, the ductility, the resilience, the toughness, and so on. So we want to engineer the material. Okay, so we want to, sometimes we want to make them stronger, sometimes we want to make the sharp knife for operation, or sometimes we want to make tools it's very very strong, or for the building, or but sometimes we want to make soft, like only for I don't know, maybe making a bridge, or not bridge, maybe just ordinary for spoon, for example, and so on. So we have a strengthening mechanism. Let me check time here. Okay, so I think still some time. So I'm gonna explain to you, there are three types of how we can strengthening the metal. Okay, for example, this is steel, the same steel that you have, but we want the steel to be very very strong. Okay, we want steel to be very very strong because this is need to crush the ores. Okay, so this is called the jaw crusher. So the jaw crusher is like, so they crush the all the rocks here to be like smaller material here, and we need the steel to be very very hard and able to crush the rocks, and then to be able to wear resistance. Or we want the steel, but the steel is actually, we want a ductile, it should be very very quite soft, and then for some application, for example, we have a pigging. So pigging is a type of equipment inside a pipeline, and the pigging, there is a pig launcher and then the pig receiver. So if you have a very long pipeline, 100 kilometers, 50 kilometers, and you want to clean the pipe, so we send a pig launcher. By the pig launcher we send the pigging, it's called a pigging like this, and this will like brush around the pipeline, so it will clean all the mold, all the corrosion, or all the scaling on the pipeline. Okay, so we need the brush should be very strong but also quite ductile, and like a brush. Okay, so here the ductility also required the pipe cleaning of the brush. Okay, so how we adjust between the stronger metal and also the more ductile metal with the similar metal. Okay, so that is that we're going to talk for today or tomorrow. Okay, so in engineer often need design alloys with high strength, yet ductility and toughness as well. And then usually if we increase the strength, the ductility will be decreased or will be sacrificed. Okay, there are three types of hardening techniques. Okay, I'm gonna just explain quite maybe fast for this one. The first one is actually by reducing the grain. So we can make the grain stronger by decreasing the grain. Okay, because why? Because if we have a smaller grain reduction, we will there would be a lot of grain boundary. Okay, and if there is a grain boundary, when you have the deformation and you have the dislocation, go to the slip plane there, and then it will be like a barrier. Okay, So because of the two grain have different orientation, a dislocation passing from grain A to grain B must be change its direction. Okay, when it change the direction, it will need some energy. So it's gonna be stronger. So the metal will be stronger. Okay, and the atomic disorder within the grain boundary result in discontinuity of slip lanes. Okay, from one grain to one another. Okay, so look like tertahan ya. So that means if you have a small grain boundary, that would be, so that means you will have more grain boundary, and then it will be stronger. How to decrease the grain boundary? We can change the process. Usually we can change the process. For example, we call it faster or something, yeah, with some processing. I will let you know later. The second one is by adding alloys. Okay, by the alloys, the solution strengthening. If you add alloys, there would be one. For example, this one is smaller than the others, so there would be some strain around here. Or if we have add one more alloys like larger than the previous one, it also will make it bigger compared to the other. It will also impose some lattice strain. Okay, so I think I'm gonna go straight to here. This is the picture between a tensile strength and the nickel content, between the nickel and copper. Okay, so the alloys paduan, yeah, between. So if you increase the nickel content, so this is a pure copper tembaga, yeah. The tensile strength is only maybe 220 megapascal, but if you add or increasing the nickel content periodically, it will increase up to more than almost 2 times, yeah, up to 400 something. Okay, so that means actually by adding the alloys, so the alloys is actually added it to the copper nickel. The alloy is actually added to increase the properties. So you see that the tensile strength is increasing, yield strength is increasing, and of course it will be sacrificed by the elongation. Well, the elongation will be decreasing with the increasing nickel content. And the third one is using strain hardening. Yeah, the one that what I explained to you before about how to stretch them. Okay, and the stretch by stretching is called strain hardening. Strain, which is we make a strain on this one. Hardening, we will dikeraskan. So strain hardening, pengerasan dengan regangan. Okay, so a very famous example of strain hardening is when we have those half form of aluminum can, and then we stretch them. So it's also gonna be increase the properties. Okay, and it is called cold work. Okay, it's called cold work because it is cold. Okay, it's at a cold temperature or a room temperature and work. So dikerjakan pada temperatur rendah. Okay, because why? Because the most metal harden at room temperature. Okay, and then the percent degree of plastic deformation, we can call it as a percentage of cold work. It is defined as the initial or original area minus the final area after deformation, because if you stretch them, the area of deformation will will reduce. Okay, and then multiply with 100%. Okay, this is a famous example of influence of this one. For example, you have this is the original one, okay, of low carbon steel. So you have those the ductility, yeah. So this is the yield strength, and then this is the tensile strength for the 0% cold work. And after that, I stretch them for a 4% cold work. So if you can see here, all the yield stress is all increasing from around to 30 megapascal up to almost 400. Okay, And if you increasing again to 24% cold work, you even can reach almost 600 megapascal, almost 3 times of the original one. But however, the if you look at here, here the elongation will decrease from almost 0.25, only maybe 0.12. Okay, so if you look at also the area under the curve, the toughness also decrease. Okay. All right, so that is one example. So okay, this is just I think I'll continue again tomorrow more about this one. Now let's open your EduNext, okay, and then let's have a look on the quiz. Okay, so you can open your EduNext. Okay, so here you will see it start from 11:30 to 12:10. So you can try to open any book. Okay, you can open the reference book and also the slide handout. I'll give you until 12:10. Okay, if you can't answer number D, that's fine. Let's skip number D, yeah, because you just learned this one, the cold work. But if you can answer all of them up to C, but if you don't answer number D, that's fine. Okay. Alright, so try your best, put in a piece of paper, or if you want to write on a tablet, that's fine as well. Please send me about, let's have a 30-minute quiz, and then around 12:10. Okay, so you should have you should have access this one, yeah. Okay, anyone? So I think I can stop share, and also I think we can close the Zoom meeting. But before that, do you have any questions regarding the quiz?
Excuse me, Miss Winnie, if I cannot, if there's problem, can I send to email or the submission of the quiz?
Oh,
In
okay.
case there's problem, yeah.
Yeah, you can. So you can, let me see. I think you can just send me, or MS Team. MS Team is much better, yeah, rather than at least I can read it in my spare time. Okay, but try to do. I have a set. So let me check again the edit assignment. So you should know. So I check it up to 12:10, but it is allowed overdue submission. So if you have like overdue submission like 5 or 10 minutes, that's fine. Okay, and then you need to submit a file required for PDF, and yeah, I think that should be fine. Okay. All right, everyone, try your best, and then yeah, I'll see you again tomorrow.